of structure and bonding, things that you've learned in general chemistry, concepts like electronegativity that we talked about a little bit at the end of the class last time. And we're going to begin to use these concepts to think like organic chemists. In short, we're going to review how to draw things like Lewis structures and molecules and calculate formal charges. But we're going to do so with some organic chemical compounds and really begin to start to think about the molecules that we work with. Some have been sort of rules-based in the sense that you learn initially how to draw Lewis electron dot structures by counting up electrons and putting them together. But then some of it's pattern-based too. Once you get the hang of it, you're going to see, oh wait, this is a carbonyl, I know how to draw a carbonyl. This is an alcohol, I know how to draw an alcohol. So we'll have these rules initially to fall back on. So last time we were talking about bonds, and we said most of the bonds of relevance to organic chemistry are covalent bonds. And then we further divided these into polar covalent bonds, non-polar covalent bonds. Remember we said polar covalent bonds generally have a difference in electronegativity of less than about 2, and it's always a little fuzzy. Ionic bonds, by contrast, have a difference in electronegativity of the 2 atoms involved, typically greater than 2. And then if it's less than about a half, less than about 0.5, we'd say a bond is pretty much non-polar. So it's important to have a grasp of some fundamental electronegativities. And the great thing about being an organic chemist rather than an inorganic chemist or a physical chemist or learning general chemistry is we have a very small view of the periodic table. So most of us in organic chemistry, I mean, there are plenty of elements out there, but we've got hydrogen and some of the alkali metals, and maybe magnesium, and carbon, oxygen, nitrogen, the halogens, sulfur, maybe phosphorus. And so I want to talk about those elements and also show you some trends. What I'm going to do is to jot down electronegativities of the elements that I typically worry about. Probably at this point in your education, it's worth actually committing these numbers to memory. Certainly by the time you come along to say where somebody like Johnny or Buck is in their education, they know these trends well enough, they're going to look and say, oh, carbon-lithium bond, that's a polar covalent bond. They may not remember that it's an electronegativity difference of 1.5, but they'll certainly have the gist of it. So let's take a look. We have hydrogen is, of course, the first element in the periodic table. And its electronegativity is 2.2 on the Pauling scale. As we move down the alkali metals, of course, they're much more electropositive than hydrogen. So lithium is 1.0, sodium is 0.9. They're all very electropositive. And potassium is 0.8. Now, let's, again, keeping with sort of our view of the periodic table. So we're seeing something here. We're seeing that as we move down the periodic table, our electropositivity increases, or conversely, as we move up the periodic table, our electronegativity increases. So I'll draw this arrow here. And let's see what happens as we move across the periodic table. So let's go from lithium, let's skip all the way over across. We'll forget about, for now, beryllium, which is a relatively unimportant element. So we'll skip boron, which is a concern to chemists typically beyond the sophomore level. So let's go directly to carbon here, nitrogen, oxygen, and fluorine. Carbon, the electronegativity is 2.5. Nitrogen, it's 3.0. Oxygen, it's 3.4. And fluorine, it's 4.0. So our electronegativity increases as you go across the periodic table. And that's nice to know, because that means even if you happen not to remember the electronegativity of carbon and the electronegativity of oxygen, you'll know that when you have a bond between carbon and oxygen, the oxygen has a partial negative charge. The oxygen is delta negative. The dipole points from carbon to oxygen. Now remember, we saw this trend of as you go up the alkali metals, our electronegativity increases, and that's the same in the halogen. That's the beauty of the periodic table. You have trends that really pervade. So as we go from fluorine to chlorine to bromine to iodine, your numbers go 4.0 for fluorine, 3.2 for chlorine, 3.0 for bromine, and 2.7 for iodine. I'll throw in one more element. As I said, I could throw in boron, which is of some relevance, phosphorus, which is of some relevance. I'll throw in just one more that you'll encounter this academic year, and actually we'll encounter later in today's talk. So sulfur is 2.6. Again, this trend, as you go up, you go increasing electronegativity as you go from sulfur to oxygen. All right, let's take these numbers and that idea we talked about last time of ionic bonds having an electronegativity difference of greater than about 2, and covalent bonds less than about 2, and nonpolar covalent bonds having it sort of less than 0.5. Let's take a look at some chemical compounds. So let's start with some simple stuff that you'd see in G-Chem. Hydrogen fluoride, we've talked about before, just about as polar as you can get. Hydrogen is 2.2, fluorine is 4.0. So we have a big molecular dipole, a big bond dipole, which in the case of hydrogen fluoride happens to be the same as the molecular dipole because it's diatomic, pointing from hydrogen to fluorine. This is just the same concept that we said last time, that we have our delta negative on fluorine and our delta positive on hydrogen. We looked at carbon dioxide last time. Let's take a look at it in light of our electronegativity numbers. So we said carbon was 2.5, oxygen was 3.4. And so you have bond dipoles pointing from carbon to oxygen. What about the molecule itself? Is there any net molecular dipole? No. Why not? They cancel. Right, exactly. So we have bond dipoles, but no molecular dipole. So hydrogen fluoride is a polar molecule. Carbon dioxide is a nonpolar molecule. And then just for the sake of contrast, I think last time I put up sodium chloride and magnesium oxide. So we said they were ionic compounds. Now I've given us some electronegativities, and we have 1.0 for sodium, or rather 0.9 for sodium, and 3.2 for chlorine. And so this fits with our concept of greater than 2 electronegativity as an ionic compound. Same thing with magnesium oxide. Where magnesium, I said, was about 1.3, and oxygen was about 3.4, so it makes sense that it's an ionic bond. Later on in the class, you'll be encountering compounds where you have a bond between carbon and magnesium. These are a class of organometallic compounds called Grignard reagents. Organometallic compounds means compounds where you have carbon bound to a metal atom. And you can already tell me, is a Grignard reagent something like methyl magnesium bromide? Don't worry about the MgBr part. But is the bond between the methyl group, that's between the carbon, I'm already writing like an organic chemist here, we'll get to that in a moment. Is that a covalent bond or an ionic bond? Covalent. The electronegativity of carbon is 2.5, the electronegativity of magnesium is 1.3, it's less than about 2. So this would be a polar covalent bond. All right, let's try our hand with a real organic chemical. One of the smallest, formaldehyde. I'll be good. I'll even draw in my lone pairs of electrons, and so forth. Where have you heard of formaldehyde before? Biology. Do they still use it? Yeah. So formaldehyde was the classic compound for preserving specimens. It reacts with all sorts of groups like DNA, cross-linked proteins, it kills bacteria. It's great at killing everything, including people. It's also carcinogenic, so the vapors are very bad for you. So nowadays substitutes are found. But it's one of the smallest organic compounds, and it's a nice example for starting with looking at bond dipoles and molecular dipoles in organic compounds. As a knee-jerk reaction at this point, most people in the room will probably know their electronegativities well enough to know, okay, all of the bonds in this molecule are covalent, not ionic. If we want to get a little more detailed, we could say 3.4, 2.5, 2.2. So we could say, we would call this bond, the CO bond, a polar covalent bond. And the CH bonds, for all intents and purposes, are nonpolar covalent. The main bond dipole in the molecule is going to be the CO bond dipole. There are also a couple of small bond dipoles from the CHs. Not very important. But the overall result is that you have a net molecular dipole, like so, pointing upward to the carbonyl. All right. Thoughts or questions? Let's take a step back so we can all get on the same page and get comfortable drawing structures like this. And so I want to take a moment to review how we draw Lewis structures, Lewis electron dot structures. We'll start with something easy, then get to something a little more confusing, maybe even spend some time chewing on it. So, let's start with the molecule carbon dioxide, CO2, the one that we've been drawing a couple of times now. Remember how you do it. You pay attention only to the valence electrons in each atom. And we're going to see how many valence electrons all of the atoms bring to the table. And then we're going to try our best to arrange them so that everybody gets a complete octet. Because with the exception of hydrogen and sometimes elements like sulfur further down the periodic table, all of the elements want a complete octet. And again, with those exceptions, you can't put more than 8 electrons around your atoms. You can't have a nitrogen with 10 electrons around it, for example. All right, so our oxygen brings 6 electrons to the table. And I'll just draw them like this. Our carbon brings 4 electrons to the table, and I'll draw them like this, dots to represent the electrons. Oh, thank you. I only put 5 around the oxygen. And our other oxygen also brings 6 electrons to the table. All right, and then by whatever means we like, we can group those electrons. You can do this mentally, you can do this by drawing around them. I'll just gather them up in little circles here just to remind us that we're bringing these together. And then we can group them together and say, all right, here's our carbon. Maybe in the beginning of freshman chemistry, you would do it like this. Here are our oxygens. And I've drawn 2 pairs of electrons between the carbon and the oxygen, 2 pairs between the carbon and the other oxygen, and 2 pairs of electrons on each oxygen. But certainly, after any short amount of time, you would now be drawing these structures like this, saying, all right, that's going to, we're going to use our bonds. Each bond represents 1 electron. We'll draw our lone pairs of electrons on the oxygen. If we're good, we might even try to put them sort of at 120-degree angles to represent the sp2 hybridization, although at this point that's not critical. There's our CO2 molecule. Now let's try something that's a little closer to the hearts of organic chemists. We'll try methanol, CH3OH. So now we bring to the table 3H dot, 3 hydrogens, each with 1 electron. We bring together, we bring in a carbon with its 4 valence electrons. We bring in an oxygen with 6 electrons. And we bring in a hydrogen with its electron. And the first time you see it, you just say CH4O, methanol. The first time you see it, you say, wait a second, how do I put all of those atoms together? But after you start to hear these names, methanol, methyl alcohol, you realize, oh, there's a methyl group, a CH3 group. and an alcohol group, NOH group. And we'll be coming back. Remember I said there were three big concepts: functional groups, curved arrow notation, and stereochemistry in organic chemistry. We'll be coming back to these functional groups in just a couple of chapters. So let's put all of these together to make our structure of methanol. Like so. And there's our structure of methanol, a full Lewis structure of methanol. After a short time, you're going to find you're writing these things like CH3OH and just taking as a given that, oh yeah, you could expand out the methyl group, but we're not going to bother with that. So this is really how organic chemists think about structure and bonding. All right, let's turn our example now, let's turn our attention now to a little bit harder example. Let's see if we can struggle through it. All right, the little bit harder example that we're going to turn our attention to is dimethyl sulfoxide. CH3 taken twice. SO. Dimethyl sulfoxide is a laboratory solvent. It's also been used in sports medicine, although I wouldn't recommend it. People rub it on sore muscles. Maybe banned now, but certainly it used to be popular. Drives all sorts of chemicals through your skin, so it's not a good idea to actually put it on your skin, but people have claimed it gives relief. All right, let's apply the same types of principles that we used before to figure out the structure of this molecule. As I said, we quickly get the hang of writing out our methyl groups as blocks. So we can bring two methyl groups to the table. All I've done is imagine pre-grouping the hydrogens and the carbon with three of its lone pairs of electrons, leaving three of its 4 electrons, and leaving 1 electron. Our sulfur is below oxygen in the periodic table, so we know that we write sulfur just like oxygen. In other words, it has 6 electrons around it, as does our oxygen. Now we have to figure out how to put these all together. Take a moment to think about that. First thing you might think about is the idea, well, I understand can form some bonds between my methyl groups and my sulfur. Then I still seem to have my oxygen. You look and you say, how do I put this all together? Connect the sulfur to the oxygen. The oxygen has 6 electrons. It just wants 2 more. So it's happy. Connect the sulfur to the oxygen. We'll have 8 electrons. Around everybody. Everybody gets a complete octet. The sulfur could have extra electrons as well. We're going to come back to that notion because this is a molecule that's nice to chew on. We're going to come back to that notion in just a moment when we get to the idea of resonance structures and the fact that many molecules can be represented better by more than one Lewis structure, and together those comprise a complete picture of the molecule. We're going to also chew on dimethyl sulfoxide as we talk about formal charges. So let's start and try to address the concept of formal charges. Another one, I think formal charges was in general chemistry. Yeah. So let's review what formal charges means, because this is actually important for organic chemistry. Okay, so the question is, yes, can we draw a double bond between the sulfur and the oxygen? And this is one very special case because the sulfur can have 10 electrons around it. This is one very special case where you could indeed draw an extra bond. We would imagine sharing this pair of electrons. And together, these two structures, which I'll put in a big, big pair of brackets, are going to make up a more complete structure of the molecule. Now, you wouldn't know this, and I wouldn't necessarily expect you to know this, but in the case of dimethyl sulfoxide, the resonance structure on the left is actually a little more important than the resonance structure on the right. We're going to come in just a few moments, either at the end of today's class or the beginning of the next class, to cases where I would expect you to be able to say which is the more important resonance structure. Here there's a little bit of an apples and oranges comparison because the sulfur has an expanded octet in the resonance structure on the right. You have poor orbital overlap between oxygen and sulfur because they're in different rows, and so you don't have that much double bond character. But again, that gets a little beyond the scope of this course.
So it's not even
okay, definitely getting ahead. Let's get to our formal charges. You are way on top of things, and this is fantastic. So let's get down to our formal charges here. And we'll start again with some simple stuff. Now, in cases of formal charges, for you, in cases of formal examples, elements in the same row in the periodic table, everyone having a complete octet, or everyone having to suffer and not have a complete octet. It's a simpler comparison. When you get between the second and third row, between carbon and phosphorus, or carbon and sulfur, or phosphorus and oxygen, or sulfur and oxygen, it gets a little bit more complicated. Right now, what I will say is, for dimethyl sulfoxide, both of these resonance structures are correct pictures of the molecule. Together, we get a little bit more complete picture of the molecule. All right, let's start with formal charges, because this will help lay the grounds for discussing resonance structures. So, formal charge really can be thought of as a bookkeeping mechanism. To keep track of where the charge is. What do I mean? If you have a molecule, either that molecule is neutral or that molecule is charged. In other words, it's an ion. Charge comes in quanta. Your molecule can have a charge of 0, it can have a charge of +1, it can have a charge of -1, etc. Formal charge basically addresses where is the charge. So for example, probably since your very first quarter of freshman chemistry, you've seen NH4. What do we call NH4 plus? Ammonium ion. And if we expand that out to a Lewis structure, we have 8 valence electrons, which we share between the nitrogens and the hydrogens. And the molecule has a net charge. Formal charge basically is the bookkeeping mechanism of saying, where does that charge reside in the molecule? And the way we address this question is by a little game. And the game's like this. Remember how we said that in making our Lewis structure, we simply look at how many electrons every atom brought to the table. In calculating formal charge, we say, let's take all of our covalent bonds and divide them up equally, share and share alike, or break them up equally. In other words, we'll give each hydrogen 1 electron from each bond, and we'll give back the nitrogen 1 electron from each bond. And then we'll look at where the charge is. The hydrogen brings 1 unbalanced positive charge to the table, and we give it back 1 electron, so that's +1 -1, 0. So there's 0 formal charge on the hydrogen. The nitrogen brings to the table 5 unbalanced positive charges. In other words, if you count your way across the periodic table, it's number 5 across. And yet we only have 4 electrons, so we give it back -4. The net result is +1. So if we draw our structure of ammonium and assign formal charges, our formal charge is a positive charge on the nitrogen. So let's try that same approach with dimethyl sulfoxide. I'll explode all of our bonds in this same way. Look at the various atoms. The hydrogen should come as no surprise, +1, -1, 0. Did draw one electron on the carbon. So no formal charge on the hydrogen. The carbon probably comes as no surprise. +4, -4 brings to the table 4 nuclear charges. We've given it 4 electrons. So we're 0. The sulfur brings to the table, it's in the same row as oxygen, so it's +6. And yet we only have 5 electrons. So its net charge, its formal charge, is +1. And the oxygen, +6 -7 is -1. And so if in this resonance structure of dimethyl sulfoxide, we assign our formal charges, just going to write our methyl groups as CH3. Now we have a positive formal charge on sulfur and a minus formal charge on oxygen.
So when should we see more of the other resonance structures?
Great question. In dimethyl sulfoxide, it's probably about 60%. Remember, resonance structures, of course, are 2 different pictures of the same thing, both present at the same time, representing our inability within one single structure to show the distribution of electrons. In the case of dimethyl sulfoxide, because we have the bond between the double bond between the second and third row element there, that's a little bit bad. So in the case of dimethyl sulfoxide, this resonance structure is actually a little bit more important. If it were a comparison between equals, say second row elements, carbon and oxygen, then the resonance structure that had the minimum separation of formal charge would be more important. And actually, along those lines, and perhaps as one to think about on your own, I'll give you may even be in the homework. I haven't looked at which ones I assigned. Certainly this, or at least not this morning. Certainly there are similar things in the homework. On your own, why don't you think about this molecule, methyl azide, and think about what resonance structures there might be. And what the formal charge is and what importance there would be to them. That's a good one to think about on your own. All right, let me write out what I've been saying about resonance structures. Give us a couple of good examples. So what's wonderful about Lewis electron dot structures is they allow us to get a very simple picture of the structure of molecules. What's limiting about them is the distributions of electrons in the molecules are often a little bit more complicated. In the next lecture, or the following one, we'll talk a little bit about molecular orbital approaches to understanding structure and bonding. But the truth is, the bread and butter of my thinking and most organic chemists' thinking about molecules is the type of structures that we're dealing with in today's class. Now, the limitation is sometimes a single picture just isn't good enough. And we'll take a couple of examples here. One is CH3, CO2 minus, acetate anion. You've probably already seen acetate in your general chemistry class. And so I can write a Lewis electron dot structure of acetate like so. And this molecule does have a charge. The formal charge is on this oxygen. I'll write negative. And this Lewis electron dot structure implies that there's a double bond to the top oxygen and a single bond to the bottom oxygen. That there's no charge on the top oxygen and that there's a charge on the bottom oxygen. That somehow those oxygen atoms and those bonds are unequal. And this, of course, is not the case. I could just as well write a structure in which the roles are reversed. Which there's a double bond to the bottom oxygen and a single bond to the top oxygen. And that structure would be just as valid. And together, the two of them make up the best picture that I can write of this molecule using Lewis electron dot structures. It's not the structure on the left, it's not the structure on the right, it's both structures at the same time. It's not that the oxygen on the bottom has a negative charge and the oxygen on the top is neutral. It's not that the oxygen on the top is neutral, has a negative charge, and the oxygen on the bottom is neutral. It's that both oxygens have half a charge. Both CO bonds have a bond and a half in character. And the confusing thing about the term resonance structures is that we do not resonate, we do not oscillate, we do not vibrate or cycle between those structures. It's both of those structures at the same time, all of the time. As I said, the sulfur one is the one tricky one, and nobody's going to hold your feet to that the fire on it. The sulfur one's the one tricky one because the other rule that ends up fighting with that rule is that double bonds between rows, or particularly between the second row, the carbon and oxygen, nitrogen row, and lower rows like sulfur and phosphorus and chlorine and bromine and so forth, are not very good. Yes, if you have, with all other things being equal, charge on a more electronegative atom is better. Other questions? These are actually really good questions, and they're really on the mark, and this is exactly the sort of question I hear people asking every year, so you are right on the mark in asking this.
Go back to ammonium. Where does the fifth nitrogen electron go?
Where does the fifth nitrogen electron go? Well, they're all shared. So the nitrogens bring 5 electrons to the table. Your hydrogens, you'd actually put it together by bringing 3 hydrogens in and then bringing in a proton that doesn't have any electrons. But the 8 electrons in the ammonium ion end up being shared between the nitrogen and the hydrogen. Other questions? In the case of dimethyl sulfoxide, the question is how you determine which resonance structure in dimethyl sulfoxide. In the case of dimethyl sulfoxide, the good news is everybody gets a pass in this class because we have this 2 opposing rules fighting it out. As I said, the resonance structure with the separation of charges happens to be more important, but I wouldn't necessarily expect you to know that, and you will actually see people write it both ways. One last question. How do you show flow? We're going to come to curved arrows in the next lecture, and we will talk about how we can convert resonance structure. I want to show you one last resonance structure, a molecule that organic chemists love, and that molecule is benzene. Benzene was a real conundrum for organic chemists for many years of why it was so special. And you'll get to why benzene is so special in either the B or the C course. But for now, we're going to see just one special aspect of benzene. Benzene, of course, is C6, H6. The carbons and hydrogens are put together in a ring. Carbons are in a ring, the hydrogens are off the ring. We have alternating double and single bonds around the ring. And each carbon, oops, I've gone a little bit below the edge of the board there. Each carbon bears 1 hydrogen. And just as in the case of the acetate anion, benzene can be written by 2 equivalent resonance structures. One in which we have double bonds between these carbons here and single bonds between the other carbons, but then a second equivalent resonance structure again, my bottom hydrogen is just gone a little bit below the blackboard there. And that second resonance structure alternates the double bonds in the other direction. And just as in the case of the acetate anion, it's not that we have a double bond on one side and a single bond on the other, or vice versa. It's that it's both of them at the same time, all the time, and together these two pictures make up a more complete structure of the benzene molecule. All right, next time we will continue our discussion of structure and bonding, and we will move on to ideas of different types of structures in curved arrows.